Hi, my name is Miley. I'm a senior at Monarch High School, and next year I'm headed off to Duke.
Hi, I'm Brache. I'm also a senior at Monarch, and I'll be attending the U.S. Military Academy at West Point next year. And our project is the continued development of the perfusion bioreactor for cardiac tissue engineering. Think of our project as a small but necessary piece of a much greater puzzle. I'd like to start with the true stories of Alyssa and Roman. While both children are healthy and growing today, what these two children have in common is that they were both born with rare congenital heart defects. Alyssa was born with a condition called tetralogy of Fallot, and Roman here with ventricular septal heart defect. Let's take a look at what that means. Roman's condition, BVSD, involves a gap in the septum between the two lower ventricles, which means the oxygenated and unoxygenated blood from the separate ventricles are now mixing. His heart has to work significantly harder to make up for this. Now, Alyssa's condition is much more complicated, as it actually consists of 4 heart defects, including the one Roman faced, which is the one we're most focused on dealing with. These are extremely tough to have to go through. Now, the current treatment involves surgically inserting a small, very material patch to fill the hole. Here's where the problem lies. When these newborns start growing, their hearts grow exponentially, and so does that hole. So these kids have to get that patch replaced as their hole grows. The reality is that they must undergo 2, 3, sometimes 4 open heart surgeries through this process. Imagine if that was your child, and you had no choice but to put them under 4 times. There has to be a better solution.
Well, the brilliant scientists at the Jacat lab are working on utilizing stem cells to fight this. Embryonic stem cells are amazing because when they are put under the right conditions, they morph themselves to function like the cells around them. At the lab, they've used this to form fully functioning cardiomyocytes and have built them into an actual patch. The patch is a hydrogel made out of fibrin and polyethylene glycol. This combination ensures the promotion of cell growth and structural stability. In theory, prevascularized stem cells would be implanted in the patch before surgery and would then grow into the existing heart cells of the child. Here's a picture of stem cells actually vascularizing within the hydrogel and forming a desirable network of blood vessels. So, inserting a patch that fills the hole and actually grows with that hole would mean we can cut surgeries down to just one, eliminating the resources, risk, and anxiety that comes with pediatric surgeries.
However, the patch is still a work in progress, and there's no way we can just test it on real children. So how can we develop and improve this stem cell research to where it can actually make an impact on these congenital heart defects? Is there any way we could build a biologically active environment to simulate how the heart would act and test it in there? Here's where our project comes in. We are building the bioreactor that will allow us to continually test and revise the patch to get it where it belongs. Here's a glimpse at the timeline for our project. First, we need to spend a lot of time designing it with engineering goals in mind. Then, we can start testing and observing the lab as they revise their patch based on our results. Finally, and this is a long way out, it can actually be implemented in real life. Let's take a look at the design process first.
We designed the bioreactor with 3 engineering goals in mind: to simulate the conditions and functions of the heart, to seal the environment, and to ensure that everything is sterile before and during testing. So, to simulate the heart, we learned we needed to incorporate 2 concepts: shear stress and uniform flow. Shear stress is a physics property that can occur in the heart. More importantly, though, we need to ensure that when the patch is hit with cell media, that it is hit with a uniform, even flow. Next, we had to make sure everything is fully sealed, which means there's no leakage during testing, and that we actually form a tight water seal within the bioreactor. Finally, our project needs to be fully sterile so that there is no contamination affecting the patch during testing and therefore our results. To achieve this, we'll be using an autoclave to cook off any bacteria, so our product must also withstand high temperatures. This also means we need to account for excess cell media so that it doesn't pool up and overflow the patch.
So using the Onshape program, here's what the final top and bottom designs look like. We'll sandwich the two together and pump cell media down the top of it, which will flow down the center of here, where the patch will be tightly nested. We'll be using tap bolts and wing nuts on all 4 corners to close it. Now, how did things turn out for those engineering goals? Simulate, seal, and sterile. Well, we made sure to create an even, uniform flow over the patch right here. To seal everything up, we carved out space for 2 silicone O-rings to sit, which the bolts and nuts will really tighten up. We also added 2 small holes between the walls of the bioreactor so that the cell media can flow out and not just pool up. The whole product is made of Delrin, which is a really nice plastic that won't melt in the autoclave.
Now that we've looked at the design, let's see what the testing and revising process actually looks like. In order to test the patch, we'll be pumping cell media into the bioreactor and looking at the data for 2 questions. Is the structure of the patch intact? And if so, how well did the vessels align? Once we know the patch will withhold the fluid pressure, we can use immunofluorescent cell staining to actually see how well the patch is adapting to its surroundings and whether or not it is an efficient solution to our problem. The data for these questions will tell the lab where they need to revise the patch.
We also needed to keep our 3 engineering goals in mind throughout the testing process, because how would the product mimic the heart if it's just sitting on a lab counter? So we'll be simulating the temperature of the heart using an incubator, and also to mimic the pulsatile, fast and slow flow of blood by pumping the cell media in with a peristaltic pump. Before we put the patch in, we'll be testing if everything is properly sealed by pumping in water and seeing with a microscope if anything got out. After that, we'll put our product into the autoclave to kill off any bacteria before our patch goes in. Unfortunately, we could not finish our testing in the lab due to COVID-19, but we hope to do so this summer if we are permitted. Now let me be clear, our bioreactor testing is not the end-all be-all before we just go and test this in a real child. But our bioreactor will help the Jacat lab adjust and revise the patch to bring it to a point where it can undergo FDA and medical approval.
Okay, so you must be wondering, what does this bioreactor actually look like? So let's go see. Here's a clip of the CNC drilling that actually carved out the designs from a big block of Delrin. Here's our top and bottom prints, which are actually really smooth. And here's a look at the full product when it's fully sealed using the tap bolts and wing nuts. It really smushes down those O-rings when it's tightened even just a little bit, and that actually won us an award at Science Fair. We definitely could not have done this project without help from these people, so we'd like to give a big thanks to them.